Hello students, welcome to the next session regarding discussion on length of belt for cross belt drive. In the previous section, we have already discussed how to calculate the length of belt for a open belt drive. Now we go for cross belt drive. As discussed earlier, already we know that a cross belt drive is a system where the driver pulley and the driven pulley both are rotated in opposite directions. So here if you see in the figure right now, larger pulley of radius R1, it is in the rotating in clockwise direction, whereas the smaller pulley is rotating in anti-clockwise direction, which you can see right now here. Now, there are some assumptions. One is first R1 is the radius of a larger pulley. Next R2, radius of a smaller pulley. Next X. What is this X? From the center of a larger pulley to the center of the smaller pulley, that is the distance between the center of both these pulleys, it is X. Total length of the belt, if you start measuring from point F to point E, traversed by E, J, G, then GH, and coming back to point F. So this entire length is nothing but it is capital L, that is we need to calculate total length of the belt. L1, length of the belt in contact with larger pulley. So if you observe here, the belt comes in contact at this point from G to E. So this is the length of the belt in contact with the larger pulley. Similarly, L2, length of the belt in contact with the smaller pulley, that is from H, K, and F. This is the portion where the length of the belt comes in contact with the smaller pulley. Along with this, L3, which is the length of the belt which is not in contact with either of the pulleys, that is one is from E to F and that is from G to H. So if we find out all these three, L1 plus L2 plus L3, we'll get the total length of this belt. So therefore, the total length of the belt is given by this equation, that is L1 plus L2 plus L3. So we need to find the value of L1, L2 and L3. Now, starting with the first term L1. So as I told you, L1 is nothing but it is the length of the belt coming in contact with the larger pulley. So if you observe in the figure carefully, from a point that is at point G, if you observe carefully, from there the belt is in contact. So the belt comes in contact from point G, J, and up to E. So this is the thing, but it is the arc length which we need to calculate for the larger pulley. So according to this one, the arc length for the larger pulley, that is the length L1, is written as, if you observe from this point, from here, from E to this vertical line, if you observe, this is totally 180 degrees. Again, we are having some angle alpha. The same angle alpha is present on the other side also, which means we need to calculate the angle from point G to point E, which is nothing but the arc length. So this arc length is given by 180 degrees, that is pi plus alpha plus alpha. Total we get pi plus 2 alpha with the radius R1. This is the arc length for the larger pulley. Similarly, we need to calculate even the arc length for the smaller pulley also. That is nothing but the arc length for the smaller pulley. It is calculated in this fashion. So again, here also we need to find out the arc length for the smaller pulley using the same method from where it comes into contact. So now from point H, the belt comes in contact with the pulley, traveling through H, K, up to F. So now if you observe in this figure, this vertical axis, it is 180 degrees. From H to vertical line, there is some angle alpha, which is already written there. The same angle alpha is obtained on the other side also. So now the arc subtended by the point from H to F, it is thing but the arc length, we write it as, this is 100 degrees, that is pi plus alpha one side plus alpha on the other side. So totally we get pi plus 2 alpha with the radius R2. This is the arc length for the smaller pulley, that is L2. Now once we have this one, we need to calculate the further things. So as we move further, now we need to calculate the arc, we need to calculate the length L3. So to do that one, first we need to draw from point O2, that is from point O2, we need to draw a parallel line to the line EF. And at the same time from point O1, the arc, that is from point O1 to E, whatever line is there, you need to extend it to some point where this O2M meet at one point. So once they meet it here, you can see from O2, the parallel line is drawn along the line EF, and from here this line has been extended at one point. Both these lines coincide, we name it as point M. Now, if you observe through a right angled triangle, O1, O2, M, this is a right angled triangle. So this is a right angled triangle. So in this right angled triangle, we need to calculate the length of this line, that is O2M. So to need to calculate the length of the value of O2M, we need to use our hypotenuse rule, that is for the right angle triangles. So to calculate the value of O2M, how I can write O2M is the thing, but this is your hypotenuse right now, that is O12. So it becomes O2M is square root of O1 O2 square minus of O1M square. So if you observe carefully, this is hypotenuse O1 O2 whole square minus of O1M square will give you the value of other side, that is O2M. This we need to apply. So now make the substitutions in the form of the radius R1 and R2 by simplifications. Let us see what are they. So how I can write O1M, this is nothing but it is a sum of O1E plus EM. What is O1E? If you observe O1 from point 1 O1 to E, it is nothing but it is radius R1. EM is this line EM parallel to the line O2F, which means O2F is radius R2. So your equation O1M is nothing but it is sum of O1E plus ME, that is O1E is R1 and ME and O2F are same, that is R2. So therefore O1M is equal to R1 plus R2. Therefore your equation for the line O2M, it is square root of x square minus R1 plus R2 square, R2 whole square. Now we need to multiply the both numerator and denominator by x square. So when we multiply, we get this resulting equation in this format, that is square root of x square whole bracket square, x square minus R1 plus R2 whole square by x square. So if we cancel, again we get the same equation itself. Now what I will do is, I will take here the simplification once more, such that we only get 1 minus R1 plus R2 whole square by x square. Now this x square, when I take it outside of the bracket, resulting term we get it as x square bracket inside 1 minus R1 plus R2 x. This is also R1 plus R2 whole square. This is also x square. So together I write it as R1 plus R2 by x whole square. And remember, only I have taken this x square outside, that it becomes x. Remaining terms are within the square bracket, which means the power is just to 1 by 2 itself. This is our equation 5. Now This for this equation, we are applying our binomial theorem by removing the brackets, expanding the terms in the brackets. We apply the binomial theorem where we neglecting the higher powers. So when we neglect the powers present beyond this bracket, what we get the resulting term, that is 1 minus of 1 by 2 r1 plus r2 by x whole square. This regarding this binomial theorem already we have learned in your PUC classes. The same theorem I am applying here. Now, when we substitute this value in the equation number 5, our equation 5 gets reduced to this format, that is x of 1 minus 1 by 2 r1 plus r2 by x whole square. So this is the value of the line O to M. This is the value of the line O to M. Similarly, I need to apply the value for the another line, that is GH also. For GH also, I need to find the value. So already we have seen that from E to F, the same angles are substituted for both the pulleys, which means whatever the value we get for O to M, if we double the same, if we double it by same, we get even for the value of GH also, which means I can write the total length L3 is nothing but already we have one O2M here. So if I again extend this point also here in this format, see here, say I have extended this mark here. Similarly, from this point, see whatever the length O to M is there, the same length is we are getting again for this new line also, that is at this point, which means if I double the length of O to M, similarly I will get the value of even this new lines also. So therefore, what I will do is directly I will double it by using the equation which we have got for O to M. So therefore, total length L3, it is nothing but it is twice of O to M. So it is twice of O to M. So our the equation what it becomes now, 2 of x 1 minus 1 by 2 r1 plus r2 whole square by x whole square. This is the equation number 6. So already previously we have derived the value of L1, we have derived the value of L2, and now L3. All we will substitute in equation number 1 and do the simplifications. So now I am substituting all those three, L1, L2 as well as L3 in equation number 1, that is L is equal to pi plus 2 alpha R1 plus pi plus 2 alpha R2 plus 2x. So I substitute here. Now what I will do is, again I am opening this bracket by multiplying this 2x inside this, so we will get it as 2x minus R1 plus R2. This is 2x square, here 2x, so resulting term we get only here x itself. So once we are up to this one, then I open these brackets here also. So I open these brackets, we get pi R1 plus 2 alpha R1, similarly pi R2 2 alpha R2. So now what I will do here is, I will arrange these terms in such a fashion that the simplification becomes more simple, such as I will take the common terms from pi R1 and pi R2. What I get resulting here, I get it as pi of R1 plus R2. Similarly, the common terms between 2 alpha R1 and 2 alpha R2, that is 2 alpha. What I get resulting terms in terms of radius, radii I get, that is R1 plus R2, and the remaining terms are written the same itself. Remaining terms are written the same itself. Now, as we proceed with the further simplification part, it gets reduced to this format, that is L is equal to pi of R1 plus R2 plus 2 alpha R1 plus R2 plus 2x minus R1 plus R2 whole square by x. Here I need to simplify the value of alpha in terms of radii R1 and R2 and x. So again, I go back to my right angled triangle, that is O1 O2M, to calculate the value of alpha. So how it is done? So to find the value of alpha, as I told, we go back to the right angle triangle O1 O2 M. So when we go back to right angle triangle O1 O2 M, so if you observe here, this is the right angle triangle O1 O2 M. Here it is 90 degrees. So this is your angle alpha. This is your angle alpha. This is your angle alpha. So sine alpha is equal to how much we get? Sine alpha is equal to opposite side is O1 m divided by hypotenuse is O1 O2. So already we have the values of this one which are in terms of the radii, and we have already made the simplification the previous things also. So now O1 m is the thing what it is summation of O1 e plus em. O1 is the thing what it is radius R1. Similarly, em is the thing what it is parallel to O2f, that is O2f value is R2, and O1 O2 is nothing but distance between the two pulleys, that is x. So which we have made a simplifications here. So now here if you observe the angle sine alpha, it is very small in nature, which means we can write alpha is equal to R1 plus R2 by x. Now I substitute this value of equation 9 in equation 7. Then the resulting equation becomes, that is L is equal to pi of R1 plus R2 plus 2 of R1 plus R2 by x plus into R1 plus R2 plus 2x minus R1 plus R2 whole square by x. So if we observe these terms, it is nothing but it is pi of R1 plus R2 plus 2 into R1 plus R2 squaring them square by x plus 2x minus R1 plus R2 whole square by x. So you can see here there is one term gets cancelled, and the resulting equation what we get is L is equal to pi of R1 plus R2 plus R1 plus R2 whole square by x plus 2x. This is nothing but the equation to calculate length of belt for each type cross belt drive case. So this is the equation. Equation number 10 represents how to calculate the length of belt for the cross belt drive case. So once we have done with this one for the cross belt drive case, another important phenomena comes in the belt drives is that when the belt is moving over these pulleys, already I have told you, so whichever is the driver pulley, the pulling side of that belt becomes the tension side and the opposite side becomes the slack side. So also we need to know what is the tension developed in the tight side as well as slack side. That is under this particular topic, that is ratio of tensions for flat drives. So for flat belt drives. So here, if you observe in the sketch, there is a pulley, and for this pulley, there is a belt which is coming in contact from this particular point to this particular point. So this is the point where the belt is coming in contact. So already they have named that this side as tight side with tension T1, another side slack side tension T2, and this pulley is rotating in clockwise direction. So now therefore, if you make some of the assumptions such as there is a flat belt which is wound around a drive-on pulley, they have made it as a drive-on pulley. So the drive-on pulley rotates in the clockwise direction. So therefore, now T1, this is tension acting on the tight side, T2 tension acting on the slack side, and the angle of contact for the belt on the pulley. So from this end, the belt comes in contact and its contact releases at this particular end. So this total angle, they name it as theta, angle or arc of contact between the belt and the pulley. So for our analysis, what we will do here is we just take a small elemental part of the contact, that is a small elemental PQ. You can see here we have taken a small elemental of PQ, this one from, this is a small elemental PQ for our analysis. So for PQ, how much is the angle subtended now? It is a smaller angle than theta, that is delta theta subtended. So condition is the elemental length PQ is in equilibrium reacting upon some of the following forces, which can be shown in figure B here, which are shown in this figure B. So in the figure B, if you observe carefully, we have shown regarding how the forces have been analyzed by resolving them along both horizontal and vertical axis. So now, so with respect to figure B, there are some points, that is for a slack side, tension T is the acting at point T itself. This is the point. For tight side, the tension T plus delta T is acting at point Q. So there is a normal reaction force developed along which point? R by the pulley on the element PQ, and there is some frictional force developed, that is F is equal to mu R when the belt is in contact and it is acting perpendicular to the normal reaction force. That is, these are the conditions. Now, we start the analysis by resolving the forces first along horizontal forces and then along vertical forces. So for resolving, we take the help of our figure number 4.33 B itself, which is helping us to understand how the forces have been resolved completely. So at first point, resolving all the forces horizontally. So once I start to resolve the forces along in the horizontal direction, so along the horizontal direction, if you observe here from this point, the forces have been resolved. One force is T sine delta theta by 2, which is acting in this direction of this component. Similarly, off on the right side, it is also acting as for the right side, it is also resolved as T of T plus delta T into sine delta theta by 2, which is equal to the other side, that is the reaction force R. It is the reaction force R. So now, once we make the simplifications, we get it in this format. That is, opening the brackets, T sine delta theta by 2 plus delta T into sine delta theta by 2. So as the angle sine delta theta by 2, it is very less. So we can write sine delta theta by 2 is equal to almost delta theta by 2 itself. So once we write it in this form, our equation 1 gets reduced to T of sine delta theta by, that is T of delta theta by 2 plus this also becomes delta theta by 2 delta T into delta theta by 2 is equal to R. So on simplification, what the equation becomes? R is equal to, adding up them, it is 2t delta theta by 2 plus delta t into delta theta by 2. So already I was discussing that as delta theta by 2 is still smaller, we are writing sine delta theta by 2 is equal to delta theta by 2. Again with this delta theta by 2, if we include delta t, it becomes still more smaller, which means this term delta t into delta theta by 2, it is very small. Hence we are neglecting this term. That is, this term delta t into delta theta by 2, it is very smaller when compared to this one delta theta by 2. As a result, we are neglecting this term, and the resulting equation we get it as R is equal to only T delta itself, and we write the equation as R is equal to T delta theta as per equation number 2. Now, once we do this one, we go for the resolving of forces in the vertical axis. So in the vertical axis, when the forces have been resolved, they are written in this fashion. So in the vertical axis, what do we have? So as we see in the figure carefully, we have, this is vertical axis, T cos delta theta by 2 plus, that is F, which is nothing but F is equal to mu R on one side of the vertical axis, which is equal to T plus delta T into cos delta theta by 2. These are the forces which have been resolved along the vertical axis. So once we continue the simplification part, we write in this format, that is T of cos delta theta by 2 plus mu r is equal to T cos delta theta by 2 plus delta T into cos delta theta by 2. So if you see on both sides T cos delta theta by 2, it gets cancelled, and we get it as mu r is equal to delta t into cos delta theta by 2. So I was already telling in that the delta theta by 2 angle is very small, and for cos delta theta by 2, its value, you already know the cos value of 0 is 1. So as we go on smaller, so cos delta theta by 2 is very less, whose value is equal to 1 itself, which means our equation mu r is equal to, now it becomes delta t, or you can write this equation as R is equal to delta T by mu. So now once we get both the equations, we can equate them together, that is 2 and 4, and you get it as T delta theta is equal to delta T by mu, or you can write it as delta T by T is equal to mu delta. Now, as I told you, we are doing this for our elemental arc length PQ, you can integrate these terms with the limits from T2 to T1 and the angle from 0 to theta. So once we integrate, we get it in this form: T2 to T1 delta T by T 0 to theta mu delta theta, and in simplification becomes log of T1 T2 to the base E is equal to mu theta, or T1 by T2 is equal to E raised to mu theta, where mu is the coefficient of friction acting and theta is the angle of contact for the arc length between the belt and the pulley, which is the thing, but the ratio of belt tensions is represented by this equation: T1 by T2 is equal to E raised to mu theta. It is using this equation you can find out the tensions developed on the tight side as well as on the slack side. Now, there are some definitions we need to know. The first important definition is regarding the velocity ratio. So why we need to know the velocity ratio is, we have seen the examples that when a belt drive is used, there are two types of pulleys. One is a driver pulley and then is the driven pulley. So both the diameters are different, which means their speeds will also be different. So to know their speeds and their relative speeds, we are using this term known as velocity ratio. So we can write this velocity ratio as, it is the speed of the driven pulley. Keep this in mind. It is the speed of the driven pulley. This is very, very important. Ratio of the driven pulley to the speed of the driver pulley or the driving pulley. So let D1 be the diameter of driving pulley, or it is a driver pulley. D2 is the diameter of a driven pulley. N1, it is the speed of a driving pulley. N2, speed of the driven pulley. So assuming that there is no slip, which means there is slip is not occurring between the belt and the pulley. So therefore, the linear speed at every point where the belt is in contact will be the same. On the belt, it will be the same on every point of the belt. So we can write this as the linear velocity speed. We write it as pi d1 n1 is equal to pi d2 n2, because if you observe for our pulleys, that it may be the larger pulley or smaller pulley, the velocity ratio, it is written in this formula itself: pi d1 n1 is equal to pi d2 n2. So pi is the common term both sides, it gets cancelled. We get it as d1 n1 is equal to d2 n2. So this velocity ratio, also known as a speed ratio, also known as transmission ratio, as I told, it is the thing what the ratio of driven pulley. So driven pulley is which one? N2, speed of the driven pulley, to the speed of the driver pulley, which means N2 by N1 is equal to D1 by D2. Sometimes if we consider thickness of the belt, then the resulting equation, it can be written as N2 by N1 is equal to D1 plus T into D2 plus T. So remember students, whenever the velocity ratio is asked to you to calculate, it is a thing but the ratio of the speed of driven pulley. Keep this in mind, driven pulley to the ratio to the speed of the driver pulley. So in the question, you should read carefully which is the driver pulley and which one is the driven pulley. Then only you can calculate the velocity ratio. Now, another term is creep. So what is this creep? So if you observe carefully, this creep, it is describing regarding the belt which is wounded or running over this driver and driven pulley. So if you observe, as it says here, when the driver pulls the belt from the driven pulley. So now this is a driver here. This driver, it is pulling the belt from the driven pulley, which means this is nothing but it is the tight side, and this is opposite side becomes the slack side as per this figure. So when the driver pulley, it pulls the belt from the driven pulley, what happens to the belt? As it is pulling this belt, there are chances that the belt gets stretched on which side? The driver's side. So when the belt is stretching on the driver's side, correspondingly on the driven side also, there is some part of the belt it has to contract. But the belt, I have told you already that it is elastic in nature. So it stretches out. The stretching out is more when compared to the contraction. Therefore, there is the increase in length of the belt which is responsible to develop the relative motion. There is a relative motion of the belt on the pulley surface there is a relative motion of the belt developed on the pulley surface, and this relative motion or developed on the pulley surface, we call it as grip. So many times, if you don't have this grip, then the belt will not stand on these pulleys. It is immediately moving out of the pulleys. So that is the reason that when you have observed the floor mills during the maintenance part, you can observe that a worker is first putting the belt on any one of the pulleys, and then with some force by pulling action, he shifts the belt to the other pulley. That is why the formation of the term creep is developed. So if there is no creep, the belt won't stand on the pulleys. Similarly, another one term is there, slip, which is coming from the term creep itself. So slip is the thing, but the relative motion developed between the belt and the pulley is the thing, but it is the slip itself. So generally the slip we are calculating in terms of percentage. So already you have seen this equation, that is your velocity ratio. So to this velocity ratio, if you multiply this term, that is 100 minus s by 100, you will get the slip amount of how much percentage is present. Sometimes if you consider one thickness, you can write this equation in this format, that is n2 by n1 is equal to d1 plus t by d2 plus t into 100 minus s by 100, which you will get the slip in terms of percentage. Now, this is also a very, very important point that is regarding the angle of contact. So, as we were discussing that we are using a open belt drive or you are using the cross belt drive, we are saying the angle of contact plays a very important role, that is the theta. So, this angle of contact theta it is different for both the cases, for open belt drive as well as cross belt drive. So how we calculate this angle of contact theta for the both the cases? So generally when the power you are transmitting from the belt to the pulleys of different diameters, the angle of contact for a smaller pulley, we take it for our consideration. That is the reason that we took this driven pulley for discussion of the ratio of tension of belts. So why we are taking the discussion? Because the belt will first slip on the pulley which is having smaller angle of contact. So as the angle of contact is very, very less, it is at that portion itself the belt starts to slip. Therefore, the reason that for a smaller pulley also is you need to calculate the value theta using this equation. So what is this equation given here? That is 180 minus 2 sine inverse of R1 minus R2 by C. So instead of C, what you can take it as the term X also, as we have discussed for all the equations here, into pi by 180 in terms of radians. So R1 is the radius of a larger pulley, R2 is the radius of the smaller pulley, C, or you can take X also, which we have discussed for our previous discussion of the cross belt drive, that is the center distance between the two pulleys. You can write here X also, because in the previous discussion we have taken it as X. Similarly, for the cross belt drive, the same equation, but the signs are changed, that is 180 degree plus 2 sine inverse R1 plus R2 by C, or you can write it as X into pi by 180 radians. Very, very important thing, the angle theta which you are calculating here, you should be calculated in terms of radians. In degrees, you cannot consider for simplification. They have to be taken in radians itself. That is the reason we are multiplying by pi by 180. Now, the next term is initial tension in the belt. So what is this initial tension? So as we were discussing, when the belt is wrapped or wound around the two pulleys, the two ends of the belt, they are joined together tightly and they are fixed over the pulleys so as to maintain a grip between the belt and the pulley rim. So therefore, when the pulleys are stationed, that when they are rotating, they are stationed at point. So at that time, there is some amount of tension which is present in the belt, and this tension which is developed during when the belt is under stationary conditions, that kind of tension we call it as initial belt tension, which is denoted by the term T naught. So when the belt is under stationary conditions, we take the average of both the tight side and the slack side to calculate the initial belt tension, that is T naught is equal to T1 plus T2 by 2. Then another term, that is power transmitted in a belt drive. So once we have learned regarding the angle of contact, the velocity ratios, this is also very important term to understand how the power is being calculated or transmitted in a belt drive. So using the same terms, that is T1 with the tension in the tights of the belt in newtons, tension T2 is the tension present in the slack side of the belt, it is also newtons. D1 diameter of the driver pulley, it is in meters. Similarly, D2 is the diameter of the driven pulley in meters. Then the effective turning force. So the turning force, how it depends? It depends upon the circumference of the follower. And this circumference of the follower, it is a thing, but it is the difference between the tensions in the tight side and the slack side. So as we have discussed, always when the belts are under continuous motion, both the tensions T1 and T2 are not the same. That is the reason that we calculate previously the derivation, that is the ratio of belt tensions T1 by T2 is equal to E raised to mu theta. The same, because of this, that effect itself, we are calculating the turning force. So therefore, the turning force, it is nothing but a difference in both the tensions. So F is equal to T1 minus T2. So this is in newtons. If we need it in kilonewtons, divided by 1000, we get it in kilonewtons. So what is power? So for power, if we multiply or we take the product of force and the velocity, we get it in terms of kilowatt, provided the velocity should be in meters per second. So P is equal to T1 minus T2 by 100 into V will get you the resulting term in kilowatt. So this is the equation to calculate the power. And the linear velocity belt, how we are calculating this one? This is pi d1 n1 by 60, or you can use even for other pull, it is pi d2 n2 by 60 itself will get the velocity here. So some of the advantages we need to understand why we are preferring the flat belt drives. So belt drives, as I told you, we are especially using for transmitting the power when the center distance between the shafts is very large. So it can be used to transmit the power. Then here in the belt drives, you can vary the speed also. Just if you vary the diameter of the pulleys, so you can control the speed. So anybody can operate. So as a result, it is simple for in construction as well as for operation. Compared to other drives, that is the gear drives, it is having a cheaper cost, that is the lower operating cost. And as we are using only the belts and the pulleys, there is a smoothness in operation. Only the thing is, you should check the elasticity of the belt, whether it is able to absorb the shocks or not. So if the belt fails, then you have to replace it and get the new belt. Similarly, there are some disadvantages. Some of the disadvantages are, you cannot say that this belt drives are completely efficient, because we are using them only when the center distance between the shafts is very large. So if the shaft distance is very small, you cannot go for belt drives, because at that it becomes a more expensive process and becomes complex in nature. So when the shaft distance is very less, we go for the preference of the gear drives, which are going to study in the next session. So in the belt drives, there is a factor known as slip. So if you don't know the exact velocity ratio, then the possibility of slipping of the belt becomes a higher chance, and that can be a dangerous process also. So you should maintain always exact velocity ratio. Here you can transmit only some moderate power. Apart from that, the slip between the belt and the pulley, it is causing the driven pulley to rotate at lower speed. So sometimes it reduces even the power transmission also. The belt drives which are using for transmitting the power, can be transmitted only when the shafts are parallelly positioned. If the shafts are perpendicularly or inclined at some angles, you cannot transmit the power using the belt drive. So therefore, generally you can transmit the power only when the shafts are parallel in position. So this ends the discussion of the belt drives. In the next session, we will be discussing regarding the problems on belt drives. Thank you, students.